Hello and welcome to the first video of the M3 chapter, Statics of Rigid Bodies. A quick exam question on the screen here from M2 to get us going. A thin uniform wire of total length 20 centimeters is bent into the frame shown. Find the distance of the center of mass of the frame from AB. I'm going to put on a coordinate grid here. I'm going to call this the y-axis, down here x, and then if it's a wire frame, we've got 4 different pieces to consider. This piece here has its center of mass at 0, 2. This piece here has its center of mass at 2, 0. Here, a quick bit of triangle manipulation. This is 4, this is 5, so this is a 3, 4, 5 Pythagorean triple. And the center of mass here, this is 3, this is a 1.5, plus 4 is 5.5. And on the y-axis 2. Up here, if this is 4, this is 3, this then is 7, with its midpoint at 3.54, 7 centimeters long. So that's all the information we need to find the center of mass. Following our usual procedure, AB is 4 centimeters in length, so that's a relative mass in a uniform wire of 4 times its midpoint 0, 2. AD is 4 times 2, 0. C to D is 5 times 5.52. BC is 7 times 3.54. And that all has to equal the total relative mass, which is the total length, 20, times x bar y bar. Now we don't actually need y bar in this case. We just need to find the center of mass from AB. From AB is the x direction, so we need x bar. So I'll just peel off the top layer here. Gives us a nice round 60, and that has to equal 20 x bar. So x bar is equal to 3. So the distance of the center of mass from AB is 3 centimeters. The frame has mass m, and a particle of mass km is attached to the frame at C. When the frame is freely suspended from the midpoint of BC, the frame hangs in equilibrium with BC horizontal. So this is vertical down here. And we know the center of mass of the frame is 3 something. So let's put that about here, where the key piece of information about this is that the line of action of this, weight of the framework, mg, is going to go through 3 on the x-axis. That's important because it tells us this distance here is 0.5, and we know this distance here is 3.5. So if we take moments about the midpoint here, we should be able to find the value of k. Part A up here, part B in yellow, taking moments about point, let's call it point E, I'll label it on the diagram. Then if it hangs in equilibrium, we know that the anti-clockwise moments must equal the clockwise moments. Anti-clockwise, we've got the mass of the framework times g to give the weight, multiplied by the distance 0.5, and that has to equal kmg times 3.5. They cancel, divide through by 3.5, and we get k is equal to 1 over 7. In this chapter, we're going to form equations to solve problems involving static rigid bodies and determine whether a rigid body will slide or topple when it's put on an inclined plane. To do this chapter, you must have done further centers of mass, the previous chapter in the textbook. In M2, when we looked at static rigid bodies, in M2 we had a chapter of the same title. We created equations by considering moments about one or more points, resolving forces in one or more directions, and a friction equation or inequality. Also, like in the starter question, we suspended laminas and used their centers of mass to solve problems. So if you wanted to consider this a 4th point when looking at static rigid bodies, number 4 might be the location of the center of mass. In M3, you need to be able to use all of these and apply these ideas to solid bodies. And this might include calculating the center of mass first, like we had on the starter question with the framework, but with a solid body. which is why you must have done chapter 5 before you can do this chapter. I struggled to know what to put on the PowerPoint for the notes in this chapter because we haven't really done anything new yet, and yet we've already finished the notes. What this chapter does is combine all of these ideas and simply apply them to solid bodies. So we're going to jump straight into some examples, and I'll finish with an exam question. A uniform solid cylinder has radius r and height 4r. It is suspended by a string attached to a point on the rim of its top end. Find the angle between the axis of the cylinder and the downward vertical when the cylinder is in equilibrium. Okay, let's get a cylinder. It's got a radius of r and a height of 4r. It's suspended by a string attached to a point on the rim. We know the axis of the cylinder is the axis of symmetry that goes down the center like this. We also know the center of mass of the cylinder is located at its geometric center, where this is going to be 2r. From our previous work in M2, we know that the center of mass of the object, if it's freely suspended, must be vertically beneath the point of suspension. So we've got the string here, and then this must go through that center point. And I'm doing what I did in M2, where I'm not going to redraw this because my redrawing would be terrible. I'm just going to call this line the vertical line, knowing that that must go through the center of mass of the object if it's in equilibrium. The angle between the axis and the downward vertical then is this angle here, which is actually quite easy to find because we've already said we know that this distance here is 2r and this is the radius here, and that forms a nice little right angled triangle where the tan of theta is equal to r over 2r, or a half. So theta is equal to the inverse tan of a half, which is 26.56 ... to one decimal place, 26.6 degrees. I've done a cylinder in this example. The textbook does a hemisphere, but I hope you can see that for any standard solid shape, if you know where the center of mass is, you can put the vertical line on and find a triangle in there somewhere. Next example. A uniform solid right circular cone has mass m with radius r and height 3r. P and Q are opposite ends of a diameter on the circular plane face of the cone. The cone is suspended from a horizontal beam by two vertical inelastic strings fastened at P and Q. Given that the cone is in equilibrium with its axis at an angle of 45 degrees to the horizontal, find the values of the tensions in the strings, giving your answers in terms of m and g. That's a lot of information. In the textbook there's a little diagram that goes with it, but let's see if we can recreate it here. The cone is in equilibrium with its axis at an angle of 45 degrees to the horizontal. We also know it's being suspended from P and Q, 2 points on the base, which means it must look something like this. Where this angle with the horizontal is 45 degrees. So let's put P here and Q here, where the diameter goes across like that. Horizontal axis here, vertical here, so that all of these little angles here are 45 degrees. The cone is being suspended with two vertical strings, one at P and one at Q, and they're attached to a beam of some kind up here. We're trying to find the tensions in the strings. Let's call this T1, T2, and we know the center of mass of the cone is 1/4 of the way from the base to the vertex. Let's put that here, and the cone has mass m, so weight mg. Considering the four things from the notes screen in reverse order, the location of the center of mass, already on the diagram here, we know that that's 1/4 of the way from here along this axis, and we actually know how far that is because we're told that the radius is r and the height is 3r, so let me put that on as well. We've got r here and 3r down to the vertex of the cone, but I think all we're going to need is this bit, so that's 1/4 of 3r, so that's 3/4 of r. So we've got the location of the center of mass. The third thing was friction, which doesn't apply in this example. The second thing was resolving forces. That's probably going to be very helpful to resolve vertically upwards. so t1 plus t2 must equal mg. So if we can find one of these, we'll know the other one very easily. And the first thing on the list was moments. And this is going to be the thing that will help us find one of these. So if we take moments about p or q, it will take out t1 or t2 from the equation because the distances will be 0. So I'm going to take moments about q. So we're going to need to know the perpendicular distance from the line of action t1 to q. So the line of action comes down here, horizontal line along here, so this will be an angle of theta, and we know the distance of the diameter is 2r. So considering anti-clockwise moments must equal clockwise moments, anti-clockwise we've got t1 times 2r cosine theta, where theta in that case is here, and we know that theta is equal to 45. The clockwise moment is the mass of the cone itself, so we need to know this distance, and we've already got this distance here in white up to the purple line. That is r cos theta from here to here, and then we need to add on this little bit here. Using this 3/4 r here and another cosine theta, we can get that distance in there as 3/4 r cosine theta. So the force is mg, the weight of the cone, times the distance r cos theta plus 3/4 r cos theta. With theta is 45, cosine theta is root 2 over 2. So on the left we get root 2 rt1, and on the right, if I put some of that on my calculator, 7 root 2 over 8 r, where both the root 2 and the r cancels to give t1 is equal to 7/8 mg. Going back to what we said about resolving vertically, then t2 must equal 1/8 mg. And there are our two answers. So we used 3 out of the 4. We didn't use friction, but we did use the location of the center of mass, we did use resolving, and we did use moments. Third example. 2 smooth uniform spheres of radius 4 cm and mass 5 kg are suspended from the same point A by identical light inextensible strings of length 8 cm attached to their surfaces. The spheres hang in equilibrium, touching each other. What is the reaction between them? So what we've got here is 2 spheres side by side. They're being suspended from a point above the center here, so the string will come down towards the centers at an angle like this. We know the radius of each sphere is 4 centimeters, and the length of the string is 8 centimeters. What's going to be a big help here is that these are all identical, so this is a line of symmetry down the middle on the vertical. So if I consider just one side of this, we've got the center of mass in the center of the sphere, and that is going to be 5g. We're going to have a reaction on this sphere from the other sphere, call that r, that will be horizontal. We've got a tension in the string T holding the sphere up, and let me call this angle here theta. And if you were to mirror this in this line of symmetry, the same would be true over here. But because it's the same, I don't really need to worry about that side. Again, in this example, there's no friction. So thinking about the other 3, we've already located the center of mass. We now need to resolve or take moments. And I think in this case just resolving will be enough. If we resolve vertically, we're going to have t cos theta minus 5g has to equal 0 if it's in equilibrium. And resolving horizontally to the right, we're going to have r minus t sine theta must equal 0. So we've got t is equal to 5g over cos theta, and r is equal to t sine theta. So in order to get r, which is what we're being asked to find in the question, we need to know t and theta, and to find t we also need to know theta, so let's focus on theta for a second. To find theta we're going to need to look at some of these distances. We know that from here to here the center point is 4 centimeters, that's the radius of the sphere. But we also know from here to here is 8, And if you continue this line towards the center, there's another 4. So we've got a large right-angled triangle with theta, 4, and 8 plus 4. So that gives me this triangle here. A quick bit of Pythagoras tells me that this other side is 8 root 2. So from basic trigonometry, we know sine theta must equal 4 over 12, or 1/3, and cosine theta must equal 8 root 2 over 12, or 2 root 2 over 3. So putting this in here for cos theta gives us 15 root 2g over 4, and r is equal to t times sine theta, and sine theta is just 1/3, so it's 1/3 of t, which cancels down to 5 root 2g over 4. Having a third and g in a fraction there looks a little bit awkward to me, and they haven't asked for an exact value, so I will just change that into a decimal. I've used g is equal to 9.8 to give the answer 17.32, but if I use 9.8 for g, I should round that to 2 significant figures, which is 17. To finish the video, a quick exam question. A closed container C consists of a thin, uniform, hollow, hemispherical bowl of radius a together with a lid. The lid is a thin, uniform, circular disc, also of radius a. The center of the disc coincides with the center of the hemispherical bowl. The bowl and its lid are made of the same material. So we've got a hemispherical bowl, radius a, with a lid that's a circular disc. So here is our hemisphere. It's a hollow shell, and we know the center of mass of a hollow hemispherical shell is 1/2 of the radius. The radius is a, so the center of mass of this is at 1/2 a from here. On top of this hollow shell is a circular disc as a lid, and obviously the center of mass of that is at the center point. And we're trying to show that the center of mass of C, the entire container, is at a distance 1/3 from O. So here we've got O, the center of the disc. To do that, we need to find the relative masses. We've been told they're uniform, and they're made of the same material. So all I need to consider is the area, and that will give us the relative mass. The area of the disc is pi r squared, where r we know is equal to a. The area of the hemispherical shell is 4 pi r squared over 2, 4 pi r squared for a sphere divided by 2 for a hemisphere, and again we know r is a, so that becomes 2 pi a squared. I'm going to keep those as relative mass, but from our previous work you could put a row on each of these and call it the mass rather than the relative mass. And now I use my table, as usual, to find the coordinates. Before I do that, let me put the axes on here to make it clear that I'm going to choose O as my origin, which means the center of mass here is minus a over 2, and I will expect my final answer from this to be minus a over 3, which I'll have to convert into a positive distance. So we've got the relative mass here, and we're looking at the y coordinate, because by symmetry we know the x coordinate is going to be 0. Got the disk, the hemisphere, and then, although I can't really show it very easily, the full shape here. Relative mass of the disk, pi a squared, of the hemisphere, 2 pi a squared, of the total shape then 3 pi a squared. This is y bar. Center of mass of the disk is at 0, and for the hemisphere minus a over 2. So we've got pi a squared times 0 plus 2 pi a squared times minus a over 2 gives us minus pi a cubed, must equal 3 pi a squared y. We can cancel a squared and pi, which just gives us a minus a on this side, and then divide through by 3 to give the answer. Therefore the distance is a over 3 from O. So that's part A. Part B, the container C has mass m. A particle of mass half m is attached to the container at point P on the circumference of the lid. The container is then placed with a point of its curved surface in contact with a horizontal plane. The container rests in equilibrium with PO and the point of contact in the same vertical plane. Find, to the nearest degree, the angle made by the line PO with the horizontal. Okay, I'm going to quickly redraw it here. We've got our hemisphere with the disk on top. We now know that the centre of mass of this is 1/3 of A down from O. Again, I'll put my axes on here. Then we've got a particle attached to the container at point P. It's all in the same vertical plane, so I will put that here. Then it's placed in contact with a horizontal plane, and if you imagine the plane here with a mass put on the point P here, obviously this is going to tilt. But as usual, instead of redrawing it, I'm just going to shift how I draw my vertical and horizontal. So I'll draw the horizontal here, like this. So this is the horizontal. And then we know two interesting things about the vertical line through the point of contact here. The first useful thing we know is that the center point of a sphere, if you imagine the full sphere here, the center point of the sphere is always vertically above the point of contact of a plane. It can't not be. So this point is vertically above this point. The second useful thing we know is that given it's in equilibrium, the center of mass of the new system with the particle P attached must also be above that point of contact. If it were not, then it would not be in equilibrium. So our vertical line goes through both of these points and the point of contact here. And what we're trying to find to the nearest degree is the angle made by the line PO with the horizontal, this angle here. There are a few different ways you can approach this. You could take the new system, the hemispherical shell and disk from part A, where we know the centre of mass there, and attach the mass half m here at P, and then find the new centre of mass here. Or you could do what we did in the starter question and consider moments about one of these points on this vertical line here, where this centre of mass would be giving an anti-clockwise moment, this would be giving a clockwise moment, and the two would have to be equal for it to be in equilibrium. So first a quick bit of geometry. If this is theta, 90 minus theta, this is also theta. That will help because to find moments about this point, which I will call G, I need to know the distance from here to here. If I can get that in terms of theta, that will help because I can also find the distance from here to here with the help of theta. So if we do a over 3 sine of theta, we get this distance. And over here, if we do a, the radius of the hemisphere, cosine theta, because this angle is obviously the same as this one, we get this distance. Now taking moments about G, anti-clockwise must equal clockwise. The anti-clockwise moment about G is just the weight of the container, mass m, so the weight is mg, times by the perpendicular distance a over 3 sine theta. We've got mg, a over 3 sine theta, is equal to the clockwise moment, that's just the weight of p, mass half m, so we've got a half mg times by this perpendicular distance a cos theta. And then the m, the g, and the a all cancel out, which is nice because theta is the thing we're trying to find. Divide through by cos theta to give tan theta, multiply by 3 gives us this, which gives us an answer of 56.3 dot dot dot, and they want it to the nearest degree, so theta is equal to 56. And there we go. I hope that's enough now for you to have a go at the questions in exercise 6a, and maybe I'll see you in the next video for some toppling and sliding.